tomorrow and through Friday with your first real program. Also, there's a video, I think it's video 2.5, where we run through 3 different exercises of basic input-output programs. We prompt the user for input, they enter it, and then we print out, make some calculations, and then we print it back out to them. So if you're in need, if you want to prepare yourself really well for Hack tomorrow, if you haven't already started, I would highly suggest that video in Module 2. Otherwise, today we'll start on conditionals. And beyond normal input-output programs, you're going to have to make decisions at some point, or you're going to have to write code in order to make decisions, maybe complex decisions. Normally, you have the sequential control flow where it starts at the top of the program, whatever code you write, and then it goes line by line, top to bottom, left to right. You can change that process by putting in conditional statements. You can make some code execute under some conditions, or you can make different code execute under different conditions. And what we're going to start with are the 3, it's actually all one statement, but the 3 basic conditional statements: if statements, if-else statements, and then if-else-if statements. And we'll also need some basic logic, because conditions are basically something that is true or false, that the value stored in this variable is strictly greater than 10. It's either true or it's false, right? And based on that, based on whether or not it's true, you execute one piece of code. If it's false, you can not execute that code, or alternatively execute a completely different piece of code. So let's go ahead and introduce the syntax of this. It's all pretty straightforward because it uses the plain English if, else if, and the keyword else. So let me go ahead and just cut and paste this first block of code here. There we go. There we go. So this is not real code up here in the condition, that less than and that greater than sign. That condition, we'll get to logical statements here in a moment. But this is the basic syntax that you would use to write an if statement. You use the keyword if, and then you put your condition into parentheses. Those parentheses are part of the code. The less than and the greater than and the condition word there, that's not real code. Well, that's a placeholder for when we actually put in a real condition there. Then I've got an opening bracket and a curly bracket, that is. An opening curly bracket and a subsequent closing curly bracket. Everything between those is the code block associated with that if statement. And as the comments state here, this is the code that anything that you put in there is the code that will execute if the condition evaluates to true. If the condition is false, this block of code will not be executed at all. So this is a simple if statement. Execute this piece of code or don't execute this piece of code, depending on whether or not your condition is true or false, respectively. You can get a little bit more fancy. You can more general by providing by providing an else statement. So I'll go ahead and repeat what we have up there. This is block A. Right? For lack of a better term, I'll just say that it's the first block, which is executed if the condition evaluates to true. Right? Then you can put an else statement. And I'm using the keyword else here. Let me scroll up. I'm using the keyword else here, and then another opening and closing curly bracket. Let me give myself some more room. There we go. All right. And now this is going to be code block B. All right. This is code block B, which is executed if the condition evaluates to false. All right. So here you can provide an alternative. The if statement, if you just have the if statement, it's going to execute or not execute. With the if-else statement, you can have a block of code execute, or alternatively, another block of code execute. These are two what we call mutually exclusive conditions here. Either block A is going to execute or block B is going to execute, but exactly one of them will execute. It will never be the case in this situation that neither of them execute or that both of them execute. That's what we mean by mutually exclusive. If A executes, then B does not. If B executes, then A does not. They are excluding each other, and it's mutual, right? So we call that mutually exclusive. Right? So again, if-else statements are mutually exclusive, which means that exactly one of the two code blocks is executed, right? All the time, right? You're never going to have a situation where it's one but not the other, or vice versa. Right? Sorry, there we go. And you know what? Let's get rid of, that's too much text down below. There we go. I just wanted to scroll up, not to go all the way up there. All right? So again, they're mutually exclusive. And again, that condition there is just a placeholder. We haven't gotten to conditions yet. We haven't gotten to logical statements. Okay? Then you can generalize this even more. All right? I'm going to go ahead and cut and paste from what I had before here, and put in that this is block A. This is block B. But what I'm going to do is I'm going to put something in between them, an else if, excuse me, and then a second condition. I'll call the first one condition 1 and the second one condition 2. Again, opening, closing curly brackets. Right? So now maybe I won't call that last one B, since I don't want to go A, C, B. I'll go ahead and go A, B, C. So this is block B. There we go. So now I've got 3 pieces of code. Code block A, code block B, or code block C. And I've got 2 conditions. So what's going to happen here is the code is going to go top to bottom. Then it's going to start evaluating each one of those conditions. If condition 1 is true, then it executes block A. If it's false, then it goes on. It doesn't necessarily go B or C yet. It looks at that second condition. If that second condition is true, then it executes code block B. If that second condition is false, then it goes on to put code block C as the final alternative. Again, each of these 3 code blocks is mutually exclusive. Exactly one of them will execute. You'll never have any other combination, like 2 of them executing or 3 of them executing or anything like that. And the order matters. It could be that condition 1 is true and condition 2 is true. But the first condition that evaluates to true, that is the one code block that gets executed, and it's the only code block that gets executed with an if-else-if statement. Right? So again, to review, if-else-if statements are mutually exclusive. Exactly one of the blocks of code is executed, and never any other combination thereof. And order matters. The first condition that evaluates to true is the one and only one that gets executed. Right? In general, you can have as many conditions as you want with as many else-if statements. Right? In the example, I only did 3 blocks and 2 statements. So you could have 4 blocks and 3 statements, which means that you necessarily have to have 3 statements. You could have 10 blocks, which means you would necessarily have to have how many statements? So if 3 statements requires 2 if conditions, and 5 of them requires 4, how many would 10 require? 9, exactly. Right? So and it's because of that else statement. The else is the catch-all. If none of these statements are true, then we have this else at the bottom. Moreover, in general, the else block is always optional. Right? In fact, here's a secret of the if, else if, and the else statements. They're all the same. Right? Cover this. Basically, look at only this part which I'm going to highlight over here. What is that? That's an if-else statement. When I start that new keyword if, that's a new if statement. Right? So technically, there is no else if statement or else if statement. It's just a series of stitched together if statements along with an else statement. And you saw this with the first two examples here, right? On the if statement that I initially introduced, there was no else statement because it's optional, right? It's only when you put it in does it become magically an if-else statement, right? So all three of these things are basically the same thing. It's whether or not you put the else. You're always optional. It's whether or not you string together a bunch of if conditions. Okay? We'll look at a more complex example later on. But before we do that, we need to fill in that blank. Remember we had a couple blanks here, condition 1, condition 2. What can we put in there? So to do that, we're going to have to introduce some logical operators, some numerical comparison operators is what we'll start with, though. Numeric comparison operators. Right? So you can compare values stored in variables to see if they meet some criteria or condition, I'll say. Right? For example, you can have, what do we call that thing? Less than, right? Strictly less than. So let me go ahead and put that. Strictly less than. Well, what else do we have? Strictly greater than. And if you want to do you don't want to be strict about it, say less than or equal to. Well, in mathematics, what would you draw? You would draw a less than sign with a little line under it to do less than or equals, right? That's math. Search as you might on your keyboard, that's not there. So what we have to do is we have to string together two characters. And that's going to be less than or equal to, right? That's how you read it, and that's why we have less than and then the equals sign, because that's how you read it, less than or equal to. You don't mix those around. If you have equals and then less than, that's going to be a compiler error. That's not part of the language. That's not something that the compiler is going to understand. This is less than or equal to, right? And we've also got, you've got greater than or equal to. Right? So you've got two sides to these inequalities. Each side could be a variable. It could be a literal, an actual value, or it could be an expression. And we'll look at all three the three types later on in a moment here. But before we do that, let's go ahead and round this out. What else do we need? What about equality? I don't want to know that it's less than or equal to or that it's greater than or equal to. I want to know if it's exact. If the value stored in this variable over here is equal to 10. Well, normally in mathematics, you would have a single equal sign. Can we do that in code? Nope. That means, what is that? That's the assignment operator. Exactly. That's how you get values into your variables to begin with. Well, if it's already been taken, well, let's go ahead and double it up. All right? Put in two equal signs. That's the equality operator. Right? It tests whether or not the left-hand side is equal to the right-hand side. And again, it could be a variable, it can be a value, it can be an entire expression. Right? There are lots of languages that have what's called dynamic typing, where you don't have like int a or double b. Instead, a variable becomes its type becomes whatever you assign to it. And in that case, they have to have what's called loose equality and strict equality. In other words, is the value stored in this variable is somewhat equal, loosely equal to this thing over here. And then they also have a strict equality where not only does this value match this value, but their types also match. That this thing is a number and this thing is a number. That's the difference between loose equality testing and strict equality testing. It only happens in other languages that are dynamically typed. What do you think they do there to distinguish those two? Just keep adding. 3 equal signs. Exactly. So we don't have that in C. Everything is statically typed, meaning that when you create a variable, you specify its name and its type. This is an integer variable. This is a double variable. And for the lifespan of that variable, its type does not change. Right? It's not dynamic. It is static. It stays the same. Okay? Well, what about negation. What if you want to know that something is equal, maybe you also want to know that something is not equal. All right, so inequality. All right. What do you think we use here? Again, if it's mathematics, what would you write? You'd write something like an equal sign, and then what would you do with it? Span it, right? Put a slash through it. Again, try as you might, you cannot find that on your QWERTY keyboard because it predates coding by many, many years. The next best thing, however, if we've got an equal sign and this slash, well, let's just go ahead and kick that slash up so that it's vertical, and we use a exclamation point. Exclamation point is not generally, right? That's as close as you can get to something looking like this, right? It's old school ASCII art, right? You can draw pictures based on just some characters on your keyboard, and that's basically what they were doing, trying to make it look like that, right? All right. All numerical operators can act. Numerical operators can act on variables, values, which we call again literals, right? Or expressions. Right? Again, literals are hard-coded values. So let's go ahead and go into code mode here. Let's go ahead and create some variables, int a, double b, and c. Right? And let's go ahead and compare a variable to a literal. Right? I'll put in an if statement here. How should I read this? If a equals 0. What am I testing here? If a is equal to 0, exactly 0. In other words, think about it a little bit deeper. If the value stored in a at this point in my program, right? That's the true meaning, right? Is the value stored in this variable equal to 10? Right? And if it's true, then this will execute, and let's say a is 0. All right. And then we'll end the line, right? So the left-hand side is a variable. The right-hand side is a literal. I'm testing whether or not the value stored in this variable is equal to a particular fixed value. You can also compare two variables, right? If a equals b, then I'll go ahead and say printf the two values are equal. And the line, there we go. All right. So what I'm testing here is two variables. Variables on the left-hand side and a variable is on the right-hand side. And again, thinking about it deeper, at this point in the real question here is, at this point in the program that we're executing this code, is the value stored in A equal to the value stored in B? Right? Is 10 equal to 10? If not, then this won't execute. Is 5 equal to 10? Then, if not, then no, this won't execute. It all depends on the value stored in those variables. You can, but shouldn't do the following. Right? So it doesn't matter what side you generally put things on. I could have done this instead of what I did before. I could have put the 10 on the left-hand side and then done whatever I wanted to. Try reading that in English, though. Is 10 equal to A? Does that sound right? It sounds weird, right? Icky. So we're not going to do that. If you are comparing a value, a variable value, and a literal, you probably want to put like we did in the first one, where we put the variable on the left-hand side. Right? So in general, this is bad style. Right? Not only that, but what if I switched around A and B? Does that sound natural? If A equals B. Or that sounds natural. I even forced myself to do I have to force myself to do it unnaturally. If B equals A. That doesn't sound as good, right? So in general, you're going to want to conform to what sounds good in English with the ordering of your variables, right? And then you can also do compare expressions. So if b times b minus 4ac is less than 0. Printf, uh-oh. All right. What am I doing there? On the left-hand side, that's an entire expression. I've got multiplication, I've got subtraction, I've got 3 different variables as well as a literal. I'm mixing everything together. On the right-hand side, I've got a literal 0. I'm checking to see if, when you evaluate the expression on the left-hand side, is it negative, right? And of course, that's what? B squared minus 4ac. If it's negative, what do you have? You have imaginary roots, right? And so that's why we've got uh-oh here, right? You would end if you tried to do this, then and find the roots of a quadratic equation, you would end up getting imaginary roots, which is not supported generally in code, right? You can, but shouldn't do the following. If 10 is less than 20, print f duh. There we go. Right. Why shouldn't you do something like that? Let me go down here. There we go. Sorry. There. Why shouldn't you do something like that? It's never going to change, right? This is always true. 10 is strictly less than 20. You can remove that first line. You can remove that last line and not even use an if statement. No matter what, the code block within that if statement is going to execute. This is called a tautology. A tautology is something that is always true. Likewise, you shouldn't put is 10 greater than 20, right? That's always going to be false, and so this will never execute. That's called a contradiction. So don't write tautologies, don't write contradictions. You're just wasting code, right? Okay. You also have a general negation operator, right? So any logical expression can be negated with a single, there we go, exclamation point. We already saw this with the not equals sign, right? Anytime that you see an exclamation point in code, you generally read that as not. Exclamation point equals, not equals. Exclamation point whatever, not whatever. So for example, if we wanted to negate the negation of A equals B, let me put that into code, sorry. Come on. There we go. Is A, or not A equals B, but you shouldn't write that. Why? It's much easier to do what? You can always put the negation out front if you really want to, but do we have another way of saying A is not equal to B? Just not equals, right? But you shouldn't write that. You should use, say, A not equals B, right? But if you have a very complex expression, then you can go ahead and do that. Another example is going to be, suppose that the negation of, let's say, A is less than or equal to B is not, sorry, I have to go into code mode here, A is less than or equal to B, but it should instead be written as what? So A is less than or equal to B. What's the negation of that statement? A is not equal, less than or equal to B, so it's strictly greater than. So it should be written as A is strictly greater than B. Right? So, but in general, if you have a more complex logical statement that you want to negate, place a negation out front. Right? You place it out front because that's how you read it. Not less than or equal to. Not equal to. So you always say that not first. And so you always want to put the not, the exclamation point, out front. If you put it at the end, it only applies to what comes after it, not what comes before it. Okay? modulo my misspellings. Right? Usually, a negation is used with a flag variable. A variable that is used to store a value of true or false, right? And I put those into quotes here because C does not have those as words. That's not part of the C programming language to use true and false. There are some extensions that you can use to bring in those words. There are some hacks that you can do to create those words that are then recognized by the language. But we're using true ANSI C here, so there is no true and false keywords. You can't create a variable and then set it equal to true. You can't create a variable and then set it equal to false. So instead, what you do in C, any or 0 is treated as false, and anything else is treated as true, right? i.e., any non-zero value is true. Right? Usually, however, you use 0 is false and 1 is true. But 10 is true, 3.5 is true, A is true. Why? Capital A? Remember back to the ASCII text value table. It has a value of 65. 65 is non-zero, therefore 65 is true, therefore A is true. Right? Yeah. There what? There are no Boolean types in C. Right? There are some extensions that allow you to do this, but this is how you do it. Further, usually you use an int variable as a flag variable, or sometimes referred to as, you just said, a Boolean variable. So let's go ahead and take a look at an example here. Let's see, what's my example? Let's go ahead and create a flag variable to indicate if someone is a student or not. Right? What would get, let's say false, and is a student would be true. Okay. What would be a good name for this variable? To indicate that somebody is a student. Is student, right? Don't get complicated about it. Label things what they are. Is student. Probably not are student, because ARE student, because there's only one of them, right? This person is a student or is not a student. So let me go ahead and create an integer variable, is student, right? Now, how do I indicate that they are a student? They are a student. Is student, I would set this equal to what? 1, right? I could also set it equal to 10. I could set it equal to, I can't set it equal to 0.5. Why? It's an integer, right? Truncation would then make it 0. I could set it equal to -10 or -5, and all of those things would be true. But by convention, we will use 1 to indicate true. Let's go ahead and set it so that they are not a student. Right? Is student, what would I set it to? 0. False. They are no longer a student. Right? So no student discount for them. Let's go ahead and test to see if they get a student discount. If is student is equal to 1. If they are a student, and I'm going to come back and change this here in a second, printf, you get a student discount. Right? And I don't know, do you get student discounts? Sometimes. Well, I mean, so say, I don't know, not on tickets, right? Do you? Football tickets? Do you get student discounts still? Oh, okay. All right, good. A lot? Okay, whatever. No. I think no. Yeah, in fact, I would have to join the alumni for season tickets. I think I'd still have to pay the contribution to get the right to pay for season tickets. Right? But once you retire, if you're an emeritus, you still get to keep your season tickets. That's one of the few benefits of being of an emeritus. But all right, so is student here. I'm testing to see if it's 1. Is that always going to work, though? What if instead I decided to defy convention and go up above and set it equal to 10, which is still true, right? Is my conditional statement here going to work anymore? Nope, because it's going to evaluate to false, right? Is student is going to have a value of 10. 10 is not equal to 1. Therefore, they don't get the student discount and they have to pay full price. So that's not going to work. This will work, but that's only because we're following the convention. When you're using a Boolean flag variable, don't use the equals equals sign. Just simply use the variable itself. The variable is either true, non-zero, or it's false, 0. And if I put that in my condition, it's either going to be true or false, which is perfectly fine for the if statement. It's going to say that it's true, go ahead and execute this code, or it's false, or the value stored in that variable is false, don't execute this code. Yeah?
So that variable alone is the condition?
That variable alone is the condition. Yep, exactly. And if you wanted to, all those conditions that we wrote before, you could evaluate them and assign it to a variable. So you could put something like, I don't know, int foo is equal to b squared minus 4ac. Now, this would actually evaluate it, right? And it would compute the radical or whatever that's called. But I want to compare this to see whether or not it's negative. So you could put something like that, right? There. Oh, oops. Why is it not saving? Oh, I'm in the wrong screen. Sorry. Let me put this over here. I don't want to leave this anyway, but you can see it as an example. Is this expression less than 0? That's either going to evaluate to true or false, and I take that true or false and I put it into the variable. So you can assign expressions, the truth value of those expressions to variables if you really wanted to, right? But I'm not going to leave that in the notes, right? Well, how do you check to see that they pay full price? If they're not a student, how would I write that? Printf, printf, nope, pay full price. They're not a student. How do I negate something again? Exclamation point. If they are not a student. And that's how you read it. If not is student, or if they are not a student, you know, in your head, formulate the correct English. Right? All right, so those are Boolean values and negation and how you can use. You generally don't want to use doubles, by the way. Because they're imprecise, and also they're 64 bits instead of the usual 32 bits, and it's a little bit more inefficient. You also have issues like round-off errors and stuff like that you could suddenly have a truth value, and then it suddenly becomes false because it gets too small and becomes 0 or something. Just use an integer value for Boolean values if you need it. Right? You also have complex logical operators. Right? You can combine conditions, logical conditional statements, to form more complex statements using what are called connectives, right? And logical operators. For example, the logical AND is true if and only if both of its operands, that is statements, are true, right? So you all know about the basic logic. If I say this and this, right? I'm putting a connective in there, a conjunction, right? We call those and in grammar is called a conjunction. In logic, it's also called a conjunction, and it's only going to be true if this and this happens, right? We'll pull some examples here in a moment, but let's go ahead and look at the syntax. The syntax is to use ampersand, ampersand. Now, why do we use ampersand? What does ampersand really mean? It means and, right? A law firm or something. the company Johnson and Johnson. How is it? They don't put and. What do? They put an ampersand. That's because the ampersand universally means and. We use two of them, well, because we like using two of them. But if you use one ampersand, it has a different meaning. It's a bitwise operator that we're not going to get into in this class. Basically, it takes whatever value you put on the left-hand side and the right-hand side, and it looks at all of their bits and matches up all of the bits. And this bit, it's going to take an and of that bit, and then an and of the second bit, and an and of the third bit, etc., and then gives you that as a result. There are lots of little bit tricks that you can use called bit twiddling. You take these bits and you twiddle them around, and you can manipulate stuff in memory and stuff like that. We're not going to get into it that deep here. If you ever do embedded systems, you'll definitely need to know those tricks, though. All right? So it's the ampersand, ampersand. An example would be A and B evaluates to true if and only if A is true and B is true. Right? So another way of thinking about that is it evaluates to false if either A is false or B is false. Or what's the only other possibility here? There are actually four possibilities. They could both be true, in which case and evaluates to true. One or the other could be false, in which case, so true, false, or false, true, in which case it evaluates to false. What's the last possibility? They're both false, in which case and evaluates to false. Or both of them are. Right? And we'll look at a more complex example here in a second after we've got its brother here. The logical OR operator is true if at least one of its operands is true, or both are. So here, this departs from English a little bit because if somebody gives you an ultimatum or something and says, you can do A or B, or you can have cake or ice cream, what do they really mean? You've got to choose one or the other, not both, right? A logical operator OR says, yeah, that's okay if both of them are true. Yeah, you can have cake, or you can have ice cream, or you can have both. And that's what the logical OR operator means. It's not the English ultimatum understood OR. It's not. That would be called the exclusive OR, and there is a way of doing that, but we're not going to do that in this course. So the syntax here is, anybody know what those are called? Lines. Vertical lines. So the technical name for them, I think, is Sheffer strokes. Or you can call them pipes, because in Unix you can use one of them to pipe one command into another command. Any other names? I think that there are at least 2 or 3 other names, but they're vertical lines or Sheffer strokes. And there are 2 of them here as well. If you only have one of them, that is a bitwise logical OR, and we're not going to get into that. Right? They use the vertical pipes here simply because, well, there's nothing else on your keyboard that says OR to me. So that's what we use. Yeah, there.
Do you use white space in between them?
No, you do not. If you use white space, then they become a single vertical bar. That's the other name, bars. And a single vertical bar with nothing in between. What does this mean? And the compiler says, I don't understand. Compiler error. Same question?
Yeah.
OK. Yeah, no white space. So no white space on either. Right. Example, again, A or B. That's how you should read this. Is true if A is true, or B is true, or both are true. Right? And it is false only when both A and B are false. Right? So let's go into code mode here, and let's write some more complex expressions here. Let's see. We have our first game here. So I don't know if let me go ahead and create some fun variable names here instead of just A, B, C, whatever. Husker score, int Akron score, right? And I can say that if say that Husker score is greater than Akron score, and I don't know, int spread, right? And the difference, say, the Husker score minus the Akron score is greater than the spread, then printf Huskers win and you win your bet. Right? Don't worry about what that is. If you don't gamble, I don't gamble either. You do pay attention to the spread, though, of course. So there's a more complex statement there, right? If the Husker score is strictly greater than the Akron score, and the difference is greater than the spread, then this would evaluate to true, and we would get this. Now, if one is true and the other is not true, then maybe you lose your bet, right? Either the Huskers lost or they didn't cover the spread or something like that. Then this would evaluate to false. Right? Another example, we will get boring here. Int a and b. There we go. If a is greater than 10 and a is less than 20, then I don't know. Do whatever. I'm not going to bother writing a print statement anymore. When is this going to give me? Oh yeah, go ahead. Oh, that's a good question. Yes, they have a higher order of precedence, and up there I put a parenthesis on the subtraction, right? I guess I wouldn't necessarily. No, I would need it because the subtraction would come before the greater than evaluation. If I didn't put the parentheses there, then it would just simply ask whether or not the Akron score was greater than the spread, and then it would take true or false. It would take that number and then subtract true or false, and that wouldn't make any sense. You'd get a value, and something would happen, but probably not what you intended. Right? What values? Oops, I meant B. Sorry. No, I did mean A. So what values of A here will this evaluate to true? When A is strictly less than 10, and A is strictly less than 20. Good. This is a kind of a nonsensical piece of code, right? What happens here? The first condition is stronger than the second condition, right? What if A has a value of 15? It goes and compares the first one. A has a value of 15. Is 15 strictly less than 10? Nope. So the first one evaluates. Does it matter what the second one evaluates to? Nope. Because the first one is false. False and true is going to be false. False and false is also going to be false. Right? Let's look at another example. If A is equal, let's go ahead and do this. If A is equal to B and A is strictly less than 10, then do something. Right? So let's look at a couple of values here. And I don't have much. I'll just do it in comments here. Suppose that A has a value of 10 and B has a value of 10. What is the result here? It's going to be false. Why? A is equal to B, right? The first one is true. But what about the second one? Is 10 strictly less than 10? No. So this is going to evaluate to false. What about a value of 5 and B is, say, 5? What will that evaluate to? True. They have the same value, and A is strictly less than 10. So this is true. What if A is 5 and B is 10? Then what happens? Now the first one is false again. The first one is now false. The second one is true if 5 is strictly less than 10, but both of them have to be true to evaluate to true. So this is going to be false. Right? Maybe one more. What other combination should I do here? I think that's all the combinations I want to do. Right? If A is strictly greater than 10, or A is strictly less than 20. Oops. Then do something, whatever that is. Right. What values of A would this be true on? So let's try 5 first of all. And let's walk through. Remember, this is OR. 5 is strictly greater than 10. Is that true? Nope. So now we have to look at the second one because we could still save ourselves here. Not both of them don't have to be true. At least one of them has to be true. Now, is 5 strictly less than 20? Yep. So a value of 5, this evaluates to true. Let's try something else. What about something in between? Say 15. So now is A strictly greater than 10? Yes. So the first one evaluates to true. What about the second one? Who cares? Exactly. So this is true. So if I were to look at this on a number line, there's 10, there's 20. Right? The first condition here says that A is strictly greater than 10. That does not include 10, but it includes everything that way. Right? The second one says if it's strictly less than 20, so it does not include 20, but it includes everything that way. What have I included in my statement here? Everything, right? So, this is a, what do we call those again? Tautology, right? It's always going to be true. As a last example, let's say that A is equal to B or A is less than 10. Now let's go through those examples again. What if A is equal to 10 and B is equal to 10? Right? Oops, sorry. There we go. Is that going to be true or false? A is equal to B, so the first one evaluates to true. Do we need to look at the second one? Nope. But is that going to be true or false? It's going to be false. 10 is not strictly less than 10. So we've got true or false. That's going to end up being true. What if I've got A is equal to 5, B is equal to 5? Same situation there, so let's go ahead and go with 10. Right? Now, the first condition, sorry. Let me go ahead and go down. Come on. Fix it. A is equal to 5 and B is equal to 10, so they're not equal, so the first condition fails. I've got false. Now we do need to look at the second one because, again, we could save ourselves here. A is strictly less than 10. Is that true? Yep. So this will evaluate to true. Give me two values that it doesn't evaluate to true. A is equal to 10 to get the second one to be false. And then B, I can assign it anything other than 10, and I will get everything to be false. All right? Good. All right. Questions so far on this? Yeah. Good question. Let's go ahead and do an example. The question was, can you use comparison operators to test for characters? And the answer is yes, but only for characters. So let me go ahead and create a character here, initial, or let me go ahead and go with answer, right? And let's say that we set it equal to y, right? Or we could reset it equal to no, right? Only a single character, though, because we haven't gotten to strings here. If answer is equal to yes, then, I don't know, printf proceeding. Right? Do you want to, typically, especially at the command line, programs will ask you, do you want to continue, yes or no? And you just simply type y or n and then enter, right? So this is a way of checking that. Now, why does this work? Y is the x, y, z. Y is the 25th character in the English alphabet. So if A starts with capital A starts with 65, is it going to be 90? It's either 89 or 90. I don't know. It's going to have a number, right? It's going to be associated. It's either 89 or 90, and so that's the number that's stored in the variable, and we're comparing it to another number according to the ASCII text table. So at the end of the day, even though it looks like we're comparing characters, we're comparing numbers here, right? So yes, it does work. Now you can use less than, not equal, less than or equal to, but now all you're doing is looking at the table. Does the value stored in this character come before y, right? And that's not that useful. But you could do something like this. Maybe we don't assign the answer, we read in the answer, right? How do we do that again, just as a really quick reminder? Scanf. What's the formatting for a character? %C. And how do I read it in? Like this. Yeah, what am I forgetting? My ampersand. So I'm prompting them for printf, do you wish to continue? Right? End the line. And then they type in Y or N or whatever and proceeding. But suppose that they wanted to, suppose that we wanted to allow them to enter either a capital Y like I did up here or a lowercase y. How could I formulate some logic there to help them? Use an or, right? Or answer is equal to lowercase y. Then proceed. Otherwise, else, and I will show you this to you later, but you can exit a program immediately by using exit 1, right? Or exit 0 or whatever. Let me go ahead and put 0 there. Right? There's no error, and we'll talk about error later. Yeah? I have to use the double. If I use the single, we're going to get into pitfalls here in a second. That's really bad. Oh, double quotation marks will not work because that's a string. Yeah. Double quotation marks are multiple, or even if you only put one character in there, it's a different type. It will not work. No. Nope. You need to use a function called strcmp, which stands for string comparison, and we'll get into that much later on. So you cannot use equals equals to compare entire strings. Yeah.
When you were declaring variables earlier and you made it so it would equal an expression and less than 0, and that would come out in C as either true or false, would that also work with declaring the variables and using these complex operators?
Yes, yes. You could put in, let me go ahead and take this and go int condition equals, you like to put those kind of things into parentheses to collect them all together and say it's one statement. You could do something like this. But it's kind of useless to create a variable just to store it and then use the variable when you can take just take what you were trying to say and put it in the condition to begin with. Yeah?
So if the user typed in the forward yes, would it still just read that first y and ignore the
Yes, that's what would happen. And so you'd still get the same behavior, except that ES would still be in the input buffer, and if you go, which you would need to flush out to get rid of it if they did continue and you needed to read some more. Yeah. Any number period other than 0 is true. -10 is true. -3.5 is true. Capital Y is true because it's 89, right, in the ASCII text table. Capital N is true because it's some other, even though we think of them as opposites, that's not how C works, right? Okay. So some good questions there. Some of them were hinting at some of the pitfalls that you can experience. So consider the following code. There we go. I don't know why it's text highlighting, but whatever. There we go. So consider the following code. What are we trying to accomplish here? We're trying to see whether or not A lies between, on that number line over there, between 0 and 10 inclusively, right? So here, fill that in, all the way up to here, and fill that in. If A lies anywhere on this line segment here, then it'll be evaluate to true, and then we do whatever we want. That's not what's going to happen, though. The above will compile, execute, and work for certain values. But, what happens when, say, A is equal to 20? Oops, just 20. Let's walk through this. There are actually two inequality operators here. It's going to C is going to read this left to right. It's going to so it's going to ask the question: is 0 less than or equal to a? Well, a has a value of 20, so is that true or false? It's true, right? 0 is less than or equal to a, which is 20. 0 is less than or equal to 20. What is true again? What value is true? 1, right? So in most systems, it'll end up being 1. It could, in some other weird systems, it could end up being 50, a billion, a -1, whatever. But let's just suppose that it evaluates to 1. So this part right here evaluates to 1. Now what's the question? Is 1 less than or equal to 10? And is that true or false? Is 1 less than or equal to 10? Yeah, that's true. So, but a was 20. It lies over here outside this number line. Our intention was that it should evaluate to false, but it ended up evaluating to true, right? You just have to be careful. What should I have done instead? Okay, let me walk through that again. The first comparison is true, or evaluates to true. Evaluates to true. That is, 0 is less than or equal to 20. Sorry, less than or equal to 20. There we go. But true is, say, 1. So the second expression comparison evaluates to true, since 1 is less than or equal to 10. There we go. Remember, that's going to be a tautology, right? So even though we wanted it to evaluate to false. Right? So what's my solution here? I should not have written that code, should I? If I have two conditions, I want to know that a is greater than or equal to 0 and it's less than or equal to 10. What should I have done instead? Use the ampersand. Just as I said, it's a is less than or equal, or 0. A is greater than or equal to 0, and a is less than or equal to 10. So the solution is to break it up into two conditions using and. Right? And that solution would look like, here I'll just put it in one, no, okay, I'll put it in a full line here. So it would not look like that anymore. It would look like and a is less than or equal to 10. And by the way, this is one of the few times that I would say disregard what I said about the style, where on the first one you would generally want is a greater than or equal to 0, right? You want a to come first. This, however, is a range, so I think that you have a solid argument here for writing it like this, because you want the a's, both a's in the center. So this is a good style here. Right. Is there a question over there? Anywhere? Okay, that's okay. All right. The style is in the eye of the beholder. Again, what we're looking for is consistency. If you use tabs to indent your code, fine. If you use 2 spaces or 3 spaces to indent your code, fine, as long as you're always doing the same thing throughout your entire program. Right? Here's another pitfall. Consider the following code. And here, I will go ahead and cut and paste. All right. Int a is equal to 5. If a is equal to 10, then do something, whatever. Right? What's the problem? There aren't 2 equal signs here, right? My intention here by putting this in an if statement is to test, is a equal to 10? Right? And the problem, oops, the above code will compile, run, but give incorrect results. Right? Why? A equals 10 is on, what do we call that again? Assignment, right? We're assigning the value of 10 to a. In other words, we're changing it. Up above, we set it equal to 5, which is not equal to 10. So we would not expect that code block to execute. But what we're doing in that conditional statement is we're saying that a is equal to 10. Well, what is 10? 10 is true because it's a non-zero value, right? So what ends up happening is a is assigned the value 10, which is true in C. Thus, the condition evaluates to true, even though we expected it to evaluate to false. Right? Because originally we said that the value A has the value stored in A is 5, which is not equal to 10. So make sure that you are distinguishing between 1 equal signs and 2 equal signs. And make sure also that's one of the most common mistakes you see in beginning programmers. And the reason I think that it happens is because of poor font choices, or you make your screen really small so you can't see the visual difference between the equals and 1 equals and then 2 equals. Some fonts tend to run together too, and not have any spaces between those equals, so it looks like one big giant one, even though there are 2 actually there. So have a sensible default. Atom.io is pretty good on its default, but make sure that you are looking at those things. And I will show you probably next week a nice tool that you can use along with GCC. You can use GCC as what's called a linter to detect these kind of things and give you warnings about them, so that you're not always just relying on your own visualization of the code. All right, another one. Here's another gotcha. All right. What's the problem here? Yeah, the thing after the parentheses. What is that? Semicolon, right? This will compile. This will compile and run, but it will always print A is 10. Why? Where do we use semicolons again? With executable statements. This is not an executable statement. It's a conditional statement. A conditional statement after which you expect, if this is true, then I'll do this. Right? Okay, so if A is equal to 10, I will do this. What is this? Blank, right? If A is equal to 10, I will do nothing. And then that's what you told it to do, right? You didn't write an executable statement. Instead, you left it blank, and then you put a semicolon, which means this is an executable statement because I've got a semicolon at the end. But what does it do? It doesn't do anything, right? So it'll compile and run on always print A because the semicolon binds to an empty executable statement. So be careful. In none of the previous examples did we do that. They're all conditional statements. Only executable statements should have semicolons at the end of it. And again, the tool that I'm going to show you later on will be able to you'll be able to detect that kind of thing. Right? All right. One last. Oh yeah, go ahead. Ooh. Like that. Oops, not sorry. After the closing curly bracket, like that. Likely that'll be a syntax error because it'll see, or maybe not. Let's find out. This is a good mystery. Let's go ahead and try it. I'm going to go ahead and fire up REPL. Right. And let's see what it says. I'll go ahead and get rid of that semicolon there, and see, and then let's see what that semicolon does. Oh, well, okay. It's complaining about A there. Int A equals 5. And then run it. Oh, perfectly fine. Why? You can put as many as you want there. Empty statement, empty statement, empty statement, empty statement. Okay. You told me to do nothing. I'll do nothing. In fact, I'll do nothing 10 times. Right? That's, I'm sure that the compiler is getting rid of that stuff anyway. The compiler sees an empty statement. It doesn't compile that into any machine code. Sometimes you want that stuff if you're doing low-level embedded systems programming. You want a no-op, which is no operation. Don't do anything for 1 clock cycle because I'm waiting on some other buffer somewhere or something like that. Yeah.
If you have if without the curly braces, you only execute the first line, or
without, what do you mean?
Like without the curly cases.
Oh, that's a good question, and that's why I don't present it like this. These two things, well, curly brackets are optional if you only bind one statement. It's a really bad practice to get into. Always use curly brackets even if you only have one statement. So this statement right here is perfectly fine. See, the if condition will attach to that print statement. Don't do it. Because the second that you add another print statement here, printf, also have a good weekend, right? What's going to happen here? That second statement there without the opening and closing curly brackets is not bound, even though I've indented it, that indentation doesn't mean anything. Indentation is just simply style. By omitting those opening and closing curly brackets, I've only bound the if statement to the first print statement. So if a is equal to 10, then both statements will print. If a is equal to 5, then the first one will not print, but the second one will, regardless of, in fact, the second one will always execute regardless of the value stored in a, because it's not bound to the if statement. Bad practice. Don't get into that habit. It's a bad habit. Right? Always have your curly brackets even if you don't need them. Right? And that error kind of compounds with languages like JavaScript, in which there are some situations where you can omit the curly brackets. There are some situations in which you cannot omit the curly brackets, and help you if you remember which one is which. That's why it's always best practice, use the curly brackets. Right? And then you get into a programming language like Python where there are no curly brackets, and indentation does matter. And now cross your fingers that everybody's using the same indentation across different systems. Because there, your style mistake of using 2 spaces instead of 3 spaces now has led to a program error instead of just a bad style. Right? All right. Let's see. Okay. I will go ahead and do this. We only have 5 minutes left, but I'll go ahead and put this up here and talk about it. Short circuiting. Right. So, consider the logical and. A and B. When we were going through those examples, I was asking, well, the first one is false, so do we need to look at the second one? And I was hinting at what's called short circuiting here. If A evaluates to false, does it matter what the value of B is? No, because false and true is going to be false. False and false is going to be false. I don't remember what I just said, but it's going to be false. No, since the first one is always false, whether or not the second one is true or false, the entire thing is going to be false. So we don't bother looking at B at all. It does what's called a short circuit. So in electrical engineering, what is a short circuit? You've got a circuit here of power running through it. Right? And then you take a wire and you cross it from this part of the circuit down to this part of the circuit. What happens? Electricity takes the path of least resistance. Is this a circuit anymore of electrical flow? Nope. It's now a half circle of electrical flow. Right? That's where we get the term short-circuited. We're shorting out the circuit. We're making the circuit shorter. So that's what happens in code. It looks at it left to right and says, A is false, and then it's a conjunction. It's an and. Forget about B. I'm going to move on. Likewise, for a logical or, if the first one evaluates to true, does it matter what the second one evaluates to? Nope. True or false is true. True or true is true. So again, short-circuiting happens. Right? The vast majority of programming languages do this. The vast majority of programming languages use short-circuiting in their logical expressions. And the reason, again, is, it's archaic. Think about back 40, 50 years where clock cycles mattered. You measured clock cycles in, say, tenths of seconds or hundredths of seconds instead of nanoseconds, right? If you could write a program that looks at one expression and then says, I don't need to look at this expression, and it goes on, that's way more efficient than if it has to look at this expression and this expression no matter what, right? So short-circuiting was put into programming languages 40, 50 years ago because it saved a couple of clock cycles. And when your computers are slow as molasses 50 years ago, that mattered. That was a huge speed up back then, right? It's not so much of a huge speed up now, but it's still in the languages because it's familiar, right? Programmers have come to expect that behavior. And they've come up with what are called idioms in order to exploit that behavior. And we'll look at several idioms later on, but basically, one example would be checking to see if a value is null before evaluating its expression. This is a safe operation. This is a dangerous operation if this is not true. So the one thing you can do is you can short circuit it by doing the safe operation, and if it says, whoa, that would be a dangerous operation, then short circuiting doesn't do that operation. And we'll come back to that when we look at pointers and null pointer checks. But it's something to understand because it's in every single programming language for the last 50 years. If somebody were to come up with a programming language that did not have short circuiting, I can guarantee you people would find that weird, odd, and they would try to immediately remedy that by saying, no, you need to do short circuiting because it's in every programming language. All right, reminder, there is no Monday class because of Labor Day. So the next time I'll see you is a week from today, Wednesday. We still have lab and hack next week, Tuesday and Thursday. No, yeah. I assume everyone. Yeah. Yeah. Say what?
The optional thing.
Which?
Like remember.
Yeah, that's just optional. If you want to.
I have some questions.
Okay. Oh yeah, sure.
So I finished it and it works,